You're building the next big AI e-commerce platform. You start with a single Node.js application handling everything. Eventually, you add new features like browsing products, adding items to cart, checkout, and even a payment service. You and your buddy, Claude, can handle anything, all in one codebase, one deployment, and one server. At first, everything is perfect. You ship features fast, your traffic is growing, and you can finally afford that Claude Max subscription plan. Oh yeah! But Black Friday looms around the corner. Traffic starts to spike, cloud bills are through the roof, but browse and search are getting 100x more traffic and other features. Yet you can't scale them independently. You have to scale the entire monolith, including the parts that don't really need it. Even worse, a critical bug fix for search services is blocked because the payment team is testing a risky feature. With one deployment pipelines, everyone is bottlenecked to the speed of the slowest team. We're not gonna deal with this anymore, you say. We're gonna split everything up right now. So we break our application down into multiple services: users, payments, inventory, search, checkout, etc. Each service handles a specific business function and communicates with each other through APIs. Each service can be deployed and scaled independently. Teams are also able to choose their own tech stacks that meets their specific needs. This allows teams to update individual components without actually affecting the entirety of the ecosystem. But what are we gonna do about our monolithic database? We could just leave it as is and have all the services tap into it. However, this could cause a couple of issues. Tight couplings where one service schema can actually break others, some scalability bottleneck, and we cannot optimize storage for different use cases. Why use a SQL database for a recommendation engine when database like Neo4j would be a better fit? To fix this, we can use the database per service pattern. As the name suggests, each service uses its own database. Payment service has its own Postgres instance, search service might use something like Elasticsearch, and inventory could use MongoDB. We've split our services, but now we have some new problems. How do services even know where to find each other? Payment service needs to call the user service. Hard-coding IP addresses for every connection would be a nightmare. And what happens when we need to scale up or down instances? This is where service discovery comes in. It allows services to automatically locate and communicate with each other. It uses a service registry, which essentially is a database that keeps track of all running services and their locations. Popular options like Eureka, Console, and Zookeeper. When a service starts up, it essentially says, hey, I want to register myself. I'm payment service and I located at this IP address. The registry tracks service health through periodic heartbeats. If it doesn't receive a health status, it removes the instance from the registry. Service discovery works in two ways: client-side and server-side discovery. For client-side discovery, the service making the request queries the registry directly to get a list of healthy instances, picks one using its own load balancing logic, and makes a direct call. This pattern lets the calling service be in control of the load balancing decision and can make decisions based on specific needs. In server-side discovery, an intermediary like a load balancer handles discovery. The calling service sends a request to the load balancer, which queries the registry, picks up a healthy instance, and forwards the request. This simplifies the calling client logic by centralizing the routing in one place. Let's briefly talk about load balancing. The load balancer distributes traffic across all healthy instances and continuously monitors them through health checks. When an instance crashes, the load balancer detects it and stops routing traffic there. Load balancer uses different algorithms. Some common ones are round robins, which cycle through instances in order, least connections, routes to the instance with fewest active requests, and IP hash, route clients consistently to the same instance. Alright, our service is looking pretty good, but there's still one problem we need to solve. When a user checks out, the service needs to validate the order, it needs to call the payment service to charge the card, and once the payment succeeds, we need to actually kick off fulfillment process. To do this, we need to actually create a new service. Let's call it fulfillment because we're so creative. The service is responsible for everything that happens after the payment succeeds. Now the question is, how should our checkout service communicate with this new service? We have a few options. REST API. REST uses a request response model with standard HTTP verbs and JSON payloads. It's simple, well understood, and every language has built-in support. But here's the problem. If checkout waits for fulfillment to respond, the user is stuck waiting while we generate shipping labels, update inventory, and send emails. Your customer is gonna be sitting there watching a loading spinner during Black Friday checkout. They're gonna be watching Singles Inferno instead. Not great. Also, what if fulfillment is temporarily down? The payment already succeeded, but now the checkout request fails because it can't reach fulfillment. You've charged the customer, but there's no record of what to ship. So then, what if checkout didn't call fulfillment at all? Instead, when a payment succeeds, checkout acts as a producer and publish an event to a message broker, something like Kafka. The message broker receives this event and stores it reliably. And checkout is completely done. It just returns a success to the user right away. Meanwhile, the fulfillment service is subscribed to the order complete topic. Fulfillment processes the order in the background. If it fails, the message goes back to the queue for retry. If fulfillment is completely down, message piles up in the queue and gets processed when it comes back online. This pattern decouples checkout and fulfillment service and makes it asynchronous. Okay, so everything is in order, but here's what I'm worried about. When Black Friday comes, we're going to be dealing with a lot of service errors and hiccups with our system. Let's figure out how to handle this chaos. The product catalog service has a slow, unoptimized database query that takes up over 30 seconds to respond. When the search service calls it, request piles up while waiting, eventually exhausting the search service resources and making it unresponsive. In the real world, this cascade through the chain of depending services can amplify the impact. This is called cascading failures, and it happens more often than expected. The first thing that we can consider is applying a circuit breaker to our service. When your service starts failing, either from timing out or lots of 500 errors, the circuit breaker starts counting these errors. Once it hits a certain threshold, say 30 errors in a row or 50% error rates in the last minute, the circuit breaker opens. Now, when search tries to call catalog service, the circuit breaker immediately returns an error. This prevents wasting resources on call that are likely to fail anyways. The circuit breaker stays open for a timeout period, let's say 30 seconds. After that, it enters a half-open state, where it lets a few test requests through. If those succeeds, the circuit closes and normal operation resumes. If they continue to fail, it opens again and waits another 30 seconds. Sometimes a request fails because the service is down, but other times a network packet just got dropped. A simple retry often solves the problem, but retries can also make things worse. If your catalog service is already overwhelmed with traffic and starts failing, you don't want every client to immediately retry. Otherwise, you just double the load on an already struggling service. The solution is exponential backoff with jitter. When a request fails, you wait before retrying. But instead of waiting a fixed amount of time, you wait exponentially longer with each retry. This gives the struggling service some time to recover. The jitter parts means adding some randomness to the wait time. Instead of every client retrying at exactly 1 second, you randomize it between 500 millisecond to maybe 1500 millisecond. You also need to set a max number of retries, say 2 or 3 times before you give up and return an error. Retrying forever just wastes resources. Now, not all operations should be retries though. You need to determine which is applicable. For example, if you've charged a customer credit card already, you definitely do not want to retry that and accidentally charge them twice. This is why Payments API uses idempotency key, a unique identifier for each transaction. If you retry with the same key, the payment service knows that it's a duplicate and won't charge twice. Some operations are naturally idempotent, while others need explicit handling. In a monolith, debugging was straightforward. You have one application, one set of logs, and one database. If a request fails, you just check logs, find the errors, and fix it. But in microservices, a single user request might touch 10 different services. When checkout fails, is it the checkout service, the payment service? You really need visibility into your entire system. First, you need all your logs in one place. Tools like ELK Stack, Elasticsearch, Logstash, Kibana collect logs from all your service into a centralized location. But having all logs in one place isn't enough. You need to be able to correlate them. This is where trace IDs come in. When a request enters your system, a unique trace ID is generated often at the entry point, like an API gateway, and attached to the request. Every service that handles this request extracts the trace ID and includes it into its log statements. When checkout service calls payment service, it forwards the trace ID along with it. Now every log entry from every service for this user request shares the same trace ID. This lets you reconstruct the entire execution flow of a request across your system. Centralized logging with trace IDs shows you what service is logged, but we can also take it a bit further and use distributed tracing to visualize the request flow and timing. Tools like Jaguar or Dynatrace use the same trace ID concept, but also track detailed timing information. When a service receives a request, it records when it's starting processing, when it calls other services, etc, etc. This gives you real-time information of how your services behave. Okay, wow, that was a lot of information to take in, but we managed to turn our single server application into a real-time microservices design pattern. I definitely did not cover everything about microservices. Some topics like deployment strategy, Saga Pattern, command query responsibility segregation, etc. would have been good to cover as well. Instead, here are some links for you to read about it in the description below. As mentioned earlier, the next video is going to be about API designs. I hope that you will check that out as well. As always, thank you so much for watching and see you in the next one.